Okay, guys, so I'm going to start off today's lesson by talking a little bit about what it is we're actually going to be doing this last quarter in STEM class. So if you look up here at the screen, I have a little presentation we're going to be going through today. And the first thing I'm going to talk to you about is what our plan is for fourth quarter. So we are going to be starting today learning about something called computational thinking. Because this last unit that we're going to be learning about is all about learning how to code, how to program, the logic behind it. Ultimately, your end goal is to create a working video game that you conceptualized and came up with yourself. So if we're talking about coding and programming, which is a huge part of STEM in 6th grade, 7th grade, and 8th grade, we have to start off by talking about something called computational thinking, and that's where we're actually going to be starting today. After that, we are going to learn about programming logic with a programming environment called Scratch, which some of you might already have experience with. Some of you might not. But if you do have some experience with it, I promise I'm going to show you some things that are going to challenge you. If you don't have any experience with it, I'm going to start right there at the beginning with you, holding your hand and taking it you through it step by step by step. After we learn about basic programming logic, you're going to have the tools that you will need in order to come up with and build and program a video game. So the last part of this unit is going to be about designing that video game that you're kind of envisioning in your mind. If we have any time left over at the end of the school year, we'll spend it doing some career exploration. I have some contacts in the game design field that might be willing to have kind of a virtual meeting with us. So I'd like you guys to hear about some opportunities if, programming or game design is something that you're really enjoying and you're really into. Okay, so with that being said, we're going to jump right into today's lesson, which is all about computational thinking. And today on our agenda, our objective, you're going to apply computational thinking strategies to solve complex problems. So you're going to learn about some strategies today, and then you're actually going to use them to solve some complex problems in a game that I picked out for you. So our essential question is, how can I use computational thinking to solve complex problems? A copy of this PowerPoint will be available in Google Classroom. So if you want to look over it at the end before you start your assignments, you can feel free to do that. So the first thing I want to talk to you about is what a complex problem is. And it's not a complicated definition. A complex problem is just a problem that is not easy to solve or to understand, at least not at first. And probably a lot of the problems you encounter in your daily life, you could say were complex problems, meaning that they might take a second for you to figure out how to solve them or fix them, or even how to understand them. But that's basically what a complex problem is. Something else we would say was definitely a complex problem would be computer programming. Computer programming is basically telling a computer what to do, giving it step-by-step instructions. So anytime you're doing something like that, that's a complex problem. And there are strategies that you can use that can help you approach that problem. So when we talk about computational thinking, we are talking about a set of techniques and approaches that people use to solve problems. In fact, you may have heard this term before because they talk about it a lot in math, okay? And it's even part of your standards in math class. They're just techniques and approaches you can use to help you solve problems. It is a way of thinking. So computational thinking is a way of thinking, and it helps you solve those complex problems a lot more easily. So once you learn about these 5 strategies, you can call upon them at any time whenever you're faced with a problem to try to figure out how to solve it. And why computational thinking is so important for programming is because this is a type of thinking a programmer or a coder would use to figure out how to express solutions to problems in ways that are easy for another human to understand or for a computer to understand. So computational thinking helps you figure out how to solve problems in a way that you can teach other people or other things how to solve it for you. So if you're a little bit confused, just hang with me. Hopefully it'll all make sense in a little bit. So one thing I want to clarify, though, is computational thinking is not thinking like a computer. Kids always get that mixed up and they think, oh, computational thinking is thinking like a computer. No, it's not thinking like a computer because really computers don't think. All they do is they follow instructions. It's not thinking like a computer. Computational thinking is thinking like a computer programmer, okay? That's really what it is. So there are different modes or strategies for computational thinking, and they're big words. Okay, they're a bunch of $5 words, but they are all super useful, and a lot of them you probably already do. I'm just trying to get you to use them consistently all the time whenever you're faced with a problem, especially when it comes to STEM problems and coding. Here are the 5 modes. First one is decomposition. Second one is pattern recognition. Third one is abstraction. Fourth one is algorithmic thinking. And the last one is evaluation. Okay, so some of those words might sound a little familiar from your math class. So let's talk about the first strategy, decomposition. Decomposition is a word you might have heard before, maybe like when you're watching like crime, shows. Decomposition is a word they use in biology to describe when like a living thing breaks down, right? Like, a plant or an animal dies and it kind of returns back to the earth. They call that decomposition. But what decomposition means is you're taking something and you're breaking it down into smaller pieces. So a lot of times people do this with problems, right? Here's an example. Let's say, because we're talking about computer programming, right? Let's say that we're in the future sometime. Let's say it's 50 years in the future. And in the future, people have these little robotic assistants that help them out with their daily tasks, okay? But whenever you get your little robot, because everybody likes things done a little bit differently, your robot is like a clean slate. You have to teach it how to do everything the way you like it to be done, right? So when you take your little robot out of the box, the first day you have it, you want it to make breakfast for you. But you have to remember, your robot doesn't know anything. You have to teach it how to do everything. So you tell it to make you breakfast. It says, okay, but how do I make breakfast, right? That's too big of a problem for the robot to understand. So you have to decompose it or break it down into smaller pieces, right? So you might say, okay, well, to make breakfast, you have to make oatmeal and you have to make orange juice. But your robot, who doesn't know anything, is probably going to ask you, how do I make oatmeal? How do I make orange juice? You have to decompose the problem a little bit more. So to make oatmeal, you have to boil water and you have to stir in oatmeal. And to make orange juice, you have to cut the orange and you have to squeeze the orange, right? But again, your robot is going to not understand that. You're going to have to decompose it more. How do you boil water? Well, you get a pot, you fill it with water, you turn on the stove, right? Decomposing is whenever you take a big problem and you break it down into its smallest pieces. All right, so the very last branches of this tree here, these are your smallest pieces. That's decomposition, right? And we use this in problem solving all the time. So let's say you had a problem, you're planning a birthday party. Well, planning a birthday party has to be broken down into smaller tasks. You have to find out where the birthday party is going to be held at. What's everybody going to eat at the birthday party? What's everybody going to do for entertainment at the birthday party? You have all these smaller problems that make up this larger problem. That's decomposition. Everybody with me? Okay. The second mode of computational thinking is called pattern recognition, and this is where you're looking for similarities among and within problems, right? So you're looking for things that are the same in one problem, or you're looking for things across multiple problems that might be the same. Here's another example. Remember our robot friend? Well, it's mid-afternoon, you're feeling a little bit thirsty, you want the robot to make you some tea, right? Again, we're gonna have to do like last time, we're gonna have to decompose the problem. And if you guys look at the little chart I have up here, to make the tea, you've got to boil water, you've got to steep the tea, you have to add milk, right? And then we've decomposed that even further. But if you look at this really, really carefully, you should recognize a pattern. Maybe not inside the problem, but between this problem and another problem we gave the robot. Can anybody recognize a similarity between this problem and the last problem that we gave the robot? If you were really observant, you probably noticed that both to make breakfast and to make tea, a robot has to boil water, right? To boil water, they need to boil water to make the oatmeal, and here they've got to boil the water to steep the tea, okay? So this is a pattern. By recognizing that pattern, you can simplify your instructions from this to this by just telling it to boil water, right? your robot already knows what that means. You taught it to do that when you taught it to make breakfast. It's a similarity, right? So now when you say make tea, you can just say robot boil water, and the robot knows what that means. Okay, so that would be using pattern recognition to help you solve a problem. Let's talk about the next one, which is called abstraction. So if you guys look on the screen, this was like the coolest game whenever I was your age. There were these books that came out. They were called Where's Waldo books. You may have heard of them before. They were basically these picture books. Didn't really have a lot of words, but it would just be this crazy chaotic scene, and your job was to find this little character named Waldo in the scene. And Waldo was this guy with this red and white striped shirt, and he had walked with a cane. He had little glasses and a little beanie cap on, and you'd have to scour every single inch of the page to try to find him. Now, this was just a small little corner of the page. In reality, it would be like 10 times this on your page. So you had to look at a lot, and you had to look really closely. Can you spot Waldo on the screen? Okay. For those of you still looking, I'm going to show you where Waldo is. Waldo is located right up here. And some of you may have found him, right? And you probably had a strategy that you used to help you find him. For me, and I know for like all of my friends, our strategy was to look for the red and white stripes. So we'd scan our page looking for red or white stripes. And once we found red or white stripes, which you can see it here, and you can see it here, and you can see it a couple other places, after that, we would start to narrow down some of the other features. Like, okay, red and white stripes, but does he have the hat, right? No hat. Okay, let's look, at something else. But we would always start with that one thing and use that as we kind of filtered through the picture. And that's what he looks like right there. So you can see his red and white striped shirt. And there he is right here. Okay. This strategy, this technical term for this strategy is called abstraction. And this is where you try to filter out any unnecessary detail to help you solve a problem, right? Because sometimes, I don't know about you, but if I have a big problem, sometimes I can get lost in all the little details. And really, to effectively solve a problem, I need to just focus on, one big thing at a time. This is abstraction. Another great example of this would be maps, right? Maps have all different types of purposes. So if you look up here, this is all showing the exact same area of Washington, D.C., right? This map is showing you metro. This map right here is showing you major roads and highways. This one is showing you the location of bike rental stations, Capital Bike Share. And this one right here is showing you the location of major tourist attractions and monuments, right? All of them are showing the same area of Washington, D.C., but they all have very different reasons for looking at them, right? For different purposes. Can you imagine if we had a map that had all of this on one? It would probably be a very confusing map to read, very difficult to read. It would have way too much information on it. So what we do is we create abstractions of maps, okay? Focusing on different important details and kind of letting everything else fall into the background. This one shows your monuments, but it doesn't show roads, highways, bike stations, or metro stops, right? By just focusing on one thing at a time, it's easier to solve your problem and get to where you need to go. This has to do with characteristics, right? A general characteristic would be a characteristic that would apply to many examples. So if we look at the boats up here on the screen, can you think of a characteristic that would apply to many of them? And you might say that it was the boat shape. You could say that seats was a characteristic that applied to many of our boats because we have seats here, seats here, seats here, seats here. You might say that paddles was a general characteristic. We have a paddle here with the canoe, a paddle in the rowboat, and what maybe we would call a paddle down here on the sailboat. Those would be general characteristics, things that apply to many examples. And then you would have specific characteristics, or characteristics that only apply to one example. Can you look at the pictures of the boats on the screen and think of specific characteristics? All right, you might say that the rowboat has 2 oars, right? Or the raft is flat. The sailboat has a sail. These are characteristics that only apply to one of them. So for example, look at cats as an example. cats have both general and specific characteristics, right? Some general characteristics of cats could be that they have tails and they have eyes and they have fur, right? These are characteristics that apply to many examples. But we also have specific characteristics. Some cats have long tails, fluffy tails, or stumpy tails. Some cats have green eyes, yellow eyes, or orange eyes. Some cats have ginger fur, black fur, tabby fur, right? They have different characteristics. But depending on what problem you're trying to solve, you might need to call on those different characteristics, right? So if I asked you to draw a picture of a cat, just any cat, draw a picture of a cat, would you need to know the general or the specific characteristics? You would need to know probably the general characteristics. You would need to know that it has a tail, eyes, and fur. On the other hand, if I asked you to draw this cat specifically, you would need to know those specific characteristics, right? Okay, well, it has, a fluffy tail, and it has yellow eyes, and it has black fur, right? So knowing which information to draw on, that's abstraction. What do you need to know? Why is it important? And you can think about this in video games and with program when it comes to, think about Super Mario Brothers, one of my favorite video games. All of these characters you see on the screen have a general characteristic that they share, something that many of them share in common, and that is that they are bad guys, right? They're all enemies of Mario. They can all cause him damage. But they all have specific characteristics as well, right? The ways that they move, and that's probably the biggest difference. Their appearances, right? Specific and general characteristics. And if you were a programmer creating this video game, focusing on those differences would help you to solve problems in your programming a lot more easily. And we'll skip over that. The last one that we're going to talk about is something called algorithm. And algorithm is a set of step-by-step instructions that plan out the solution to a problem. So once you have, applied some computational thinking strategies and you figured out how to solve a problem, your algorithm are basically your step-by-step instructions for how to do it. And being able to write an algorithm is a strategy and a skill all its own. And people have a lot of different ways of doing this. They can just write it out step by step. Programmers often call this pseudocode. So it doesn't have any specific programming language that it follows, but it tells you step by step what you're supposed to do, almost kind of in a list. That's pseudocode. An algorithm can be written sometimes even with a flowchart. For example, here's a flowchart for making tea. You start, you fill your kettle, you heat the water, you ask the question, has the water boiled? And if it hasn't, you continue to heat it, and you kind of loop through that. When the water has boiled, you make the tea, and then you stop, right? This is a simple flow chart, and it's showing the solution to a problem, how to make tea, step by step by step. Okay? Now that you've learned about these different computational thinking strategies, now it's time for you to move on to your assignments and kind of practice some of them. So you have 2 assignments this week to work on. Assignment number 1, after these resources, you're going to see a 5-question quiz on the material that I covered today. Please make sure that you do not close the quiz until you've answered all the questions. Please make sure you go through and you review this PowerPoint before you start the quiz so you can do your best. Assignment number 2 is more of a fun assignment. So I have given you a link to a game called Lightbot, and it has 3 levels with multiple stages in each level. What I'd like you to do is go through and play all 3 levels of the game. After you're done, you can come back to Google Classroom, and what you're going to do is use a little worksheet to write, a couple sentences to a paragraph describing how you use computational thinking while you were playing the game. Did you have to decompose? Did recognizing patterns help you solve the game? Did you write any algorithm? Did you have to do any abstraction? I want you to think about those computational thinking skills and tell me about how you use them to play the game.